Welcome to Section 3 of the Mastering Keras course. In this section, we're going to be looking at how to develop and implement deep generative models. And in particular, we're going to be looking at GANs and autoencoders. So I'll talk about them briefly in this introductory video. And here we'll also talk a little bit about what these generative models can do for you. And in particular, what we're going to look at them doing in this course. So we're going to look at how to implement two important generative models. We're going to look at generative adversarial networks, GANs, and these are very well known, very powerful neural network models. They're also notorious for use cases such as deep fakes. Second sort of model we'll look at, variational autoencoders. Now we're going to use these generative models to generate synthetic data, something which can be used to assist other learning tasks. So synthetic data is going to be useful to you when there is insufficient or inadequate training data available. Now, being insufficient is pretty self-explanatory. If you just don't have enough data, you need to supplement the real ground truth training data that you have with synthetic data just to have sufficient data to be able to train your deep learning models. But data can also be inadequate for various reasons. It can be that your data lacks sufficient variety, or even if you have a lot of data, you may have insufficient data of particular classes. And this is a really common problem in a lot of real-world use cases, particularly situations where you're attempting to predict positive cases that occur extremely rarely. And so for an example that I've worked on, where you're trying to predict faults in critical industrial machinery, situations where there are systems on, say, an oil rig or a manufacturing process, and you want to predict when a fault will occur in these systems. But of course, these are very sophisticated systems. People have put a lot of effort into making sure these faults don't occur. May have a lot of historical data, years or decades worth. There's likely to be extraordinarily few data cases where a fault has actually occurred. So you have lots of data, but you have insufficient positive cases. So three ways in which synthetic data is often generated. It can be that you want to generate data that are representative of plausible real-life cases that you can pre-specify how these can be generated from available data by, say, transformations. And a particularly usual case of this is with image analysis, where, for example, you can rotate the image or you can change the color and shading a little bit, because if you have a handwritten digit that's a 6, you can also obviously expect to see this digit slightly rotated or slightly moved off center, so forth. These are very simple. We know beforehand how we can generate plausible synthetic data from the real life cases by simple transformations. Other synthetic data you're going to want to use occasionally are data that's just general, that is similar to the available data in general. And this is going to be particularly the case when you simply have insufficient data. In the other situation where you've got sufficient data, but there's particular subsets or particular classes of your data that is insufficient, you're going to want synthetic data that is similar to, say, the particular class, which is of insufficient number in your available data. So we're going to be using GANs and variational autoencoders to produce two, that is to say, synthetic data that is similar to available data in general. And we're also going to be using variational autoencoders to produce three, synthetic data that is similar to a particular class or case from the available data. As well as being able to produce synthetic data, GANs can also be used to transform input data to better resemble target data. And a particularly notorious case of this is deepfakes, where you can train up GANs to take images, say, of myself and transform them to look like images of, say, Barack Obama, while doing the same thing to my audio, so that you take audio clips of me speaking and transform it to appear to sound like Barack Obama. And put this all together, you can create a fake video of Barack Obama, or what appears to be Barack Obama speaking, but really it's me speaking, and it's being transformed to a fake video where I get an image of Barack Obama to say what I want him to say. GANs are also particularly important in this course for two reasons. Firstly, the way in which we train GANs, and in particular how we train the generative component of GANs, is analogous to how we're going to end up training actor-critic models in reinforcement learning. You'll see that when we look at GANs, we will train the generative component of the GAN by training it through the discriminator component. And similarly, in the actor-critic model, we're going to be training the actor component by training it through the critic component of the model. Also, we're going to come back to GANs and see how they can be used for semi-supervised learning. Now, for those of you who aren't familiar with semi-supervised learning, supervised learning is where we have that includes input features as well as target variables. And our aim is to obtain a model that discovers the patterns between the input features and the target variables so as to be able to predict the target variable given new input features. Unsupervised learning is a situation where we have no target variables and we're simply trying to discover patterns inside the input feature data, and clustering is prototypical of this. But semi-supervised learning is where we do, once again, like the supervised case, have input features and target variables, and we want to discover a pattern between the two. But in this case, most of our training data is unlabeled. We may have labels for some, we may have known target variable values for some of our training data, but overwhelmingly, or at least in part, our training data has no labels. And we'll see how we can use GANs to perform semi-supervised learning to assist us in discovering the relationship between input features and target variables while making use of a lot of unlabeled data, which is to say historic data that has no known value for the target variables.